Okay, I think we're ready to start. Nicole, it's your stage.
Thanks. In this second lecture of my trio, we're going to start off with reviewing the homework problem, and then we're going to return to Szilard's engine, look at some other versions of it, and especially focus on quantum effects. There's a quick review of the homework. We said we should consider a ratchet with these different arms and a ball here, which is like a tooth that can catch on the arms. If we wind up the ratchets such that the next arm comes to be beneath the ball, the spring mechanism will store potential energy. And if the ratchet attempts to unwind, then this arm is going to catch on the ball, and so our ratchet won't lose the potential energy that is stored. I claimed that there's this heat path around which will kick the ratchets. So it can kick the ratchet in a winding direction, the ratchet will come to store more potential energy, but if it kicks in the opposite direction, the ratchet cannot unwind. We said the Kelvin clock statement of the second law of thermodynamics is, it is impossible to devise a cyclically operating device, the sole effect of which is to absorb energy in the form of heat from a single thermal reservoir and to deliver an equivalent amount of work. For those who had never heard of this story before yesterday, what possible resolutions did you come up with? And by the way, it is much, much better in a situation like this to put forth an answer that is wrong than not to put forth any answer at all. Because if we're afraid of being wrong, we're never going to accomplish research. Science is not going to advance. So just throw out some of the ideas and we can build on them. Yes.
An analogy could be the belief mechanism where we created one bit of information left and right to generate work on heat. I was wondering why, because the spring is in storing potential energy, there's work being done. So there must be some bit of information somewhere that's being created to get heat out.
Okay, so the proposal seems to be look around for some extra source that could be providing the extra work other than the temperature, the fixed temperature bath. Like surely there's some other resource that we're missing. And the problem that we saw yesterday, Szilard's engine, that resource was information. Maybe information is the other resource here, but in general, you're saying, I think, surely there must be some other resource that we're missing. Okay, you have another idea?
I was thinking, since the microscopic physics is time reversible, you should also have fluctuations where because of thermal fluctuations, the ball opens up and the ratchet is able to unwind. So as a net effect, there will be no binding.
Yes. Okay, so the issue here is this ratchet is in thermal equilibrium with our heat bath. So it undergoes Brownian motion, it jiggles. As I said explicitly, it'll try to jiggle back and forth. They'll be able to jiggle only in the forward direction. But just like this ratchet, also this ball is going to be small and in thermal equilibrium with the heat bath. So if this thing is subject to Brownian motion, also this thing will be subject to Brownian motion. And so occasionally it'll lift up and let the ratchet unwind. So that's kind of the standard way of thinking about this. And we can incorporate your way of thinking about this by saying, well, suppose that my ratchet really did work in the way that I described, in that it just kept storing potential energy and never unwound. It would have to be the case that this ball was at a much lower temperature so that it wouldn't be exhibiting Brownian motion. And so there would be some extra low temperature background, and that would be our secret resource. So, very good. Thanks very much. Resolution is if ratchet exhibits Brownian motion, So does the ball, which will sometimes lift up. And lets the ratchet unwind. A little bit of background about this problem. It is a pretty old problem. It's sometimes called the Brownian ratchets. And sometimes called the small company confinement ratchets. If you want more detailed analysis, then I recommend the Feynman lectures on physics. This problem appears in volume 1, chapter 46. This problem is an example of what I'd like to think of as a game that I call Why Does the Second Law Not Break? It's a fun game. You can play with friends over lunch. The one person comes up with a story that appears to break the second law, and everybody else has to figure out why it doesn't actually break, and then you switch. Also, just a general takeaway from this story is what seems like ordinary thermodynamics really needs rethinking when systems are. Second part of the lecture, the longer part, will be a return to Szilard's engine. A reference for all sorts of variants on this engine is chapter 5 of my book. From which I will draw some parts. First, let's briefly recap what Szilard's engine is all about, since we've seen a lot of lectures since then. We said, suppose we have a classical gas in a box, very, very simple single particle gas, for example. We can drop in a partition, measure which side the gas is on, hook up a weight, so that, and then unfix this partition, so that the particle will punch the partition to the other side of the box, and in the process, lift the weight, doing work against gravity. In other words, if we have information, we can use it to turn random heat into useful coordinated work. We can reverse this engine. This idea came from Rolf Landauer, who was an information scientist at IBM. He published this idea in the IBM Research Journal. In 1961. Landauer was also a skeptic of quantum computing. He thought that quantum systems would always be so difficult to control that we could never possibly harness them well enough to build a quantum computer. So hopefully he was wrong about that. But he did have very, very interesting insights about the relationship between information and energy. Here's our setup. Once again, we have a classical gas in a box. The gas is going to be this really simple gas that consists of one particle and an extremely simplified example. Now we have no idea where the box and the particle is. Its position is totally random. Again, there's some temperature heat back around with which the system can exchange heats. And we have a source of work. So we have an anvil that is high up. Our goal is to reset the particle's position to a well-known value. Let's say the right-hand side of the box. This is like taking a messy sheet of scrap paper that has been scribbled on totally randomly and erasing it to a nice, clean, well-known state. So you might say erasure. Here's the protocol. You can probably predict it based on Szilard engine. We slide the partition into the box near the left-hand wall, and then we push the partition to the box's center using our capacity to perform work. Our particle will end up trapped in the right-hand side. What does that take? Well, by a calculation very similar to the calculation that we did yesterday, we have to spend this amount of work. Why do we have to spend it? Because we're compressing a gas. The amount of work is at least Boltzmann's constant times the temperature times log 2 on average. And this inequality is an equality if the process is quasi-static, so that the gas is always in equilibrium. That's an idealization, very, very, very slow. If the process is quasi-static, then we never waste any energy, we never waste any work on roiling up the gas, getting it into a non-equilibrium state. So this work cost of erasure is at least as great as the work that we can gain from Szilard's. If you run Szilard's engine and then perform Landauer erasure, then you're kind of undoing what you did before, except if you don't perform the processes quasi-statically, then you're going to lose some work. This is in the spirit of the second law, which is sometimes synopsized as you can't win. A generalization of this conclusion is called Landauer's principle. Landauer argued that to erase a bit of information always costs work, and on average, that's at least KT log 2 units of work. Landauer presented 3 arguments for this conclusion, and he pointed out that erasure is an irreversible process logically. So erasure works no matter the initial states. The particle could have been originally here or here or here or here or here or here or here, etc. It could have been in the left-hand side of the box or the right-hand side of the box. It's always reset to the right-hand side, regardless of the initial state. That's kind of a definition of erasure. So many different states are mapped to one state. And from that final state, you cannot recover the initial states because this was a many-to-one mapping. Landauer pointed out that information is always encoded in physical systems. So he argued that logical irreversibility should go along with physical thermodynamic irreversibility for the consumption of work. And we can synopsize Landauer erasure with use of work to recover information together with the expenditure of heat. But an implication of Landau erasure is a really deep conclusion for the relationship between information processing and thermodynamics, because suppose that we want to compute, and compute, and compute, and compute. Eventually, we're going to run out of scrap paper, which we need for computations. The universe doesn't have an infinite supply of scrap paper, so we'll have to erase some. According to Landau, erasure costs thermodynamic work. So computation has an intrinsic thermodynamic cost. I learned that senior spring of college in my first quantum computation class, and I was just staggered because information and thermodynamics, energy feel like quite different things, and like they don't intrinsically have to do with each other, but they turn out really to be very much found out. Does anyone have questions about Landau erasure? No. It might just be worth pointing out, given what I just said, that Bennett has argued that logically reversible operations can be performed without energy cost. And so it is clear that it really fundamentally costs work in computation. These stories that I've been telling are of surprising significance. We've seen now Landau erasure, Szilard's engine, and Szilard's engine. Closely related is Maxwell's demon, but I don't have time to talk about that. There are references about that. These stories form tropes that you will see again and again across quantum thermodynamics and the thermodynamics of information. But very often we can take a problem that we're interested in and cast it as a Maxwell demon or Landau erasure, and then use what we know about these general problems in order to gain insights about our specific problem. Kind of like this ratchet. It would be a Maxwell demon in a sense, if it actually worked. Okay. Let's move on from classical versions of these stories to quantum ones. There are many ways in which quantum physics is brought to bear on Szilard's engine. I'm going to present a few that I particularly like. But for more information, you can check out these books and a book and a review about Maxwell's demon and these related topics. First, we have a review in Reviews of Modern Physics. From 2009. And also, Leff and Rex have written 2 books about Maxwell's demon, creatively called Maxwell's Demon and Maxwell's Demon 2. Here's one way in which a quantum Szilard engine can differ from a classical one. First, inserting a piston can cost us work. Here, again, is our box with our gas. Here's the piston. I should do a little more erasure myself, which costs not only work, but also time. particle in our box is classical, then it's localized. The box is a three-dimensional region, although I don't draw so well that I actually drew a three-dimensional region, but pretend it's three-dimensional. The particle is effectively zero-dimensional, and of course this partition, we can think of as a plane. So it's two-dimensional, so it takes up 0% of the box's volume. So the particle has no probability of being beneath the partition when it descends, and so the particle is not going to be disturbed. But a quantum particle is in some quantum states that has a wave function relative to the position eigenbasis. I'll suppose for the moment that the system is in a pure state, and of course generalized to mixed states, but this is just for simplicity. So suppose that now the box is one-dimensional because that's just easier to deal with, and the particle has a mass m. Let's draw out the modulus of the wave function. This is left-hand side of the box, this is the right-hand side of the box, this is the center point. And over here we'll have the modulus of the wave function. We know the form of the energy eigenfunction of a particle in a one-dimensional box from undergrad quantum mechanics. Let's call it psi n of x as a normalization factor. It's a sinusoid. We have n pi x over the length of the box here. For quantum numbers n equals 1, 2, and so on. And we also know the form of the eigenenergy associated with the n eigenfunction. Let's call it E sub n. And n squared, pi squared, h bar squared over twice the mass times the length squared. In terms of this basis, we will express this wave function. Of the wave function at some time t relative to the position eigenbasis is psi of x of t, and it's some linear combination with some coefficient Cn of our eigenfunctions and phase factors from time. And of course, these coefficients are complex and normalized. Suppose, to start with, that the particle is at some time, it doesn't matter what time, in an energy eigenstate associated with an even quantum number n. For example, suppose that n equals 2. That corresponds to a wave function shaped like this. And the partition is going to come down at a node. That means the particle has 0 probability of being there. The probability at the middle of the box, which is square modulus of our wave function times some infinitesimal line elements is 0. So our state is not disturbed, our particle is not disturbed, so we don't have to worry about the work cost. However, suppose that our particle is in an energy eigenstate associated with an odd quantum number, like the ground states. Now the partition is descending very much not at a node. This is going to cause a disturbance. Our probability of, or the particle's probability of being at the center is non-zero before we insert the partition, but has to vanish afterward. Therefore, we are very much disturbing our quantum system, and we are going to have to pay a work cost. The calculation of that work cost is a little involved and involves fractals, so I will direct you for details to these references. The initial idea was in a paper by Zurich. It was a Los Alamos pretense from 1984. And the problem was analyzed in a lot more detail by Bender and others in the Proceedings of the Royal Society A. That's one way in which quantum physics changes our understanding of Szilard engine. The second way I'm going to present is one of my favorite ways that quantum physics alters the Szilard engine story. It depends on particle statistics. The results I'm going to present here come from PRL by Kim and others.
Nicole, quick question. In
Yes.
the previous version, where does the temperature enter?
I wasn't referring to temperature. I said for convenience and simplicity, we'll do an analysis associated with the particles being in some energy, pure states. But we can build on that. It would take linear combinations in order to model a thermal state.
Okay, so then the thermal state would correspond to the
A mixture.
mixture.
Yeah.
Okay. Mhm.
Do a partition, you could calculate the partition function. for
Yeah.
that, and you can get the same.
But these authors make 4 assumptions as far as I could find. First, they're considering an engine of exactly 2 particles. So in our box with our partition, we have 2 particles, and they can perform work only if they're on the same side of the box. Because if they're on opposite sides of the box, then on average, the pressure that will be exerted from the right will equal the pressure that will be exerted from the left. And so the partition isn't going to go anywhere on average. Second, the authors assume that the particles do not interact with each other, although this assumption was lifted in later papers. We also assume that the temperature is very small, so in some ways, our system acts like it's in its ground states. Although things here are tricky because the system is actually in its ground state, so that T really is 0. Well, first, that's physically impossible according to the third law of thermodynamics. And second, our T in KT log 2 will equal 0. So our work extracted is not going to be a very interesting number. Fourth, we'll consider some quantum particles and some less quantum particles. If the particles are quantum, then they obey spin statistics. But kind of awkwardly actually lack spins. Which sounds weird. I didn't find any discussion about this by the authors, but it seems to be an implicit assumption. It does seem strange because we usually think of spins as giving particles spin statistics, but a chain of qubits is equivalent via Jordan-Wigner transformation to spinless fermions, so we could probably actually implement their assumption. But these are theorists who were doing abstract theory, so they were much less concerned about implementations than just in deriving their response principle. We'll study 3 cases of this 2-particle gas. In the first case, the particles are distinguishable. We will measure which side of the partition each particle is on. And there are 4 possibilities. First, particle A can be on the left while particle B is as well. Second, particle A can be on the left while B is on the right. Third, they can be interchanged. B can be on the left while A is on the right. And fourth, both particles can be on the right. All these possibilities are equally likely. And in 2 of the 4 cases, or 1/2 the cases, the particles are distributed unevenly. Therefore, the work that these distinguishable particles can perform on average should be greater than 0. In our second case, the particles are bosons. Particles are indistinguishable, so we can't label them A or B. Now there are 3 possibilities for the outcome of our measurements. We just have to measure how many particles are here and how many particles are here. Both particles can be on the left. They can be on opposite sides of the partition, or both particles can be on the right. In this case, 2 of our 3 possibilities find both particles on the same side of the partition, and so able to exert a non-zero pressure and perform work. I finally, as you can probably predict, we're going to think about fermions. Now, when we perform our measurement, we'll find only one possibility. By Pauli's exclusion principle, particles can't be on the same side of the partition.
That assumes that being on the side of the partition means having the same number, even if there are different physical locations on that side of the partition.
Yeah, we're lumping together all the, let's say, possible microscopic positions as being just 1 degree of freedom, being on the left-hand side rather than the right-hand side, because that's all we're measuring, left or right. And this is a reason why I said there's this implicit assumption that the particles don't actually have spin, because if they had spin, then 2 fermions could be here, one could point upward, one could point downward. Because pressures on average are balanced, the amount of work that these fermions can perform is 0. So what can we conclude from these 3 cases? Well, first of all, on average over trials, we can get work in 2 of the cases, and there's a hierarchy. The average work performable by bosons greater than the average work performable with distinguishable particles, which is greater than the average work performable with fermions. So bosonic statistics are actually useful in this particular example of Szilard's engine.
If we assume that these 3 probabilities are equally probable.
Yeah, and the left-hand side of the box and the right-hand side of the box are assumed to be equivalent in terms of the potential around and so on, so that there wouldn't be any other preference for being on the left-hand side or the right-hand side.
No, I mean, I don't quite get why isn't the situation where 2 bosons are on different sides more likely than localizing on one side.
Wait, can you repeat that?
So I don't quite see why the situation with the bosons isn't the same as the situation with distinguishable particles. Only now the 2 middle states are glued into one, and it's twice more likely than the 2 other ones.
It's a direct result of indistinguishability. So that over there, since the particles are distinguishable, we can assign labels to them. And if you perform these trials, then on average, you'll find cases in which the particle labeled A will be on this side, particle B will be on the other side, and also the reverse case. And the statistics will be set, they will be like that just because of the principle of distinguishability. And here, since the particles are indistinguishable, we can't separate this into 2 different cases.
I'm not saying we have to separate this. I'm saying that it's not obvious why all the 3 probabilities should be the same.
It's just a result of particle statistics.
Microscopic universe. So you equal probability assumption. Any microscopic state is equally probable, so that's a microscopic.
Yeah,
Canonical example.
we're saying there's,
Every elementary state is the same.
yeah, there's no kind of extra hidden degree of freedom that could distinguish these or make one more probable than the other. The only degree of freedom is where the particles are. And distinguishability would amount to an extra degree of freedom, but we don't have distinguishability here. So there isn't that extra degree of freedom to create a difference in the probabilities. Or if we had an energy ramp that was slanting downward, that would be a different kind of a degree of a freedom that would also create a probability difference. But we're just assuming there isn't such a degree of freedom, and the indistinguishability of particles kind of forces on us that there's nothing to separate this case from that case in probability. And something else that's done in the paper, I'll just use here, or report here, is that as the temperature approaches infinity, you would expect the quantum particles to become distinguishable. And indeed, the statistics all come to equal each other. So the particles become distinguishable and all the average work quantities come to be the average work performable by distinguishable particles. Are there any other questions about this use of particle statistics in Szilard's engine? In the red?
In the classical Szilard engine, you argue that information per scheme can be converted to work. But in this case, it seems like only certain cases are able to convert the information into work.
Right, so we're saying if we have fermions, then yeah, we can't extract work on it.
That's the information that's really stable.
Exactly.
But
Even
also-
before we measured, we would know the outcome, and so we don't gain any information.
But the second case of the boson, for example, we are gaining information, but you're saying it can't be converted into work?
It can. For the work gain on average is positive. And did you have a question?
Yeah, so, could you please explain again why T goes to infinity and the particles become distinct?
I didn't explain that, but it's because as you raise the temperature, the particles become more classical.
Oh,
Just in general, we can think about that in terms of thermodynamic length versus a quantum length, comparing them. I mentioned that the assumption about no interactions was lifted in later papers.
Particles are possible. So that's how they're able to go across the division. When they're possible.
Could you repeat that?
Because so how do you get two particles with the classical on one side of the division?
We have a gas in a box, we insert the partition, and then we measure where is each of our particles, if they're classical. So that's the protocol.
Thank you.
And since this workshop is held by an AMO institute, I feel like I should at least point you toward the references about the interactive use. Was an at least partially different team. The work is pretty recent. And there were some follow-up papers, so you could follow the citation tree if you're interested. The third and final influence of quantum physics on the Szilard story that we're going to talk about involves entanglement. Our agent, who is performing the operation, can have a memory system that's entangled with our particle. Actually, this story is a variant on Landauer erasure rather than Szilard tension directly, but one is basically a reverse of the other. These results come from a paper by Lidia Del Rio and friends, published in Nature in 2011. And with a setup. We have a system of interest S that we want to erase. This system can be correlated with some memory, which we'll call O. I don't know why they use the letter O for a memory. But our memory can be entangled with other things as well. So we'll introduce a reference R. That's everything else our memory can be correlated with. And as usual, we have around a heat bath at some temperature T, from which we can draw heat. The reduced state of our system and memory is called rho. Then I'll introduce two more states. The reduced state of O is surprisingly called rho sub O. We trace out the system of interest from the joint states, and rho sub S follows in tracing out our memory from joint state. Our mission is to calculate the minimum amount of work required to erase S, or in other words, to reset S to 0 state, which is a nice, clean, fiducial state, given that we hold some information about it. So we're going to hope to take advantage of these correlations of this information to reduce the work cost of erasing S. And I'll call this work cost W of S given. Okay, I'll also give a more specific setup in one example, and for that example, it'll be this result, but I'll give you a spoiler as to what the end result looks like. The conditional work cost is the conditional entropy of S given O times our favorite thermodynamic factor, KT log 2. And I'll define this entropy. But as a little bit of background, as we heard about from Nellie, there are many different types of entropies. There are lots and lots and lots of types of entropies. In the rest of this lecture, I'm just going to be talking about von Neumann type entropies. That is, when I write, I'll often write H of some state, let's call it sigma, and you are probably familiar with the formula. What's this conditional entropy? First, we should define it. The entropy of S conditioned on O is the entropy of the joint state minus the entropy of the reduced state of our memory. But what is its physical significance? This quantifies our uncertainty about the system of interest, given that we have access to the memory. Are probably aware that Nielsen and Chuang have written a Bible for quantum information and computation, and they have a little cartoon that they use to kind of suggestively illustrate the significance of this. They don't have a full explanation, but let me try to piece it together for you. So their illustration is of a Venn diagram. So suppose that we know the form of rho S. So we know what state our system S is in. Still, we're going to be somewhat uncertain about S. So if we, unless this is pure state, most states are not pure. So if we measure S, probably we're going to be uncertain about the outcome. And let's represent that uncertainty with one bubble. And entropy quantify uncertainties. So I'll label it with H of rho S. And we can tell a very similar story about H of rho O. This is loosely speaking our uncertainty about the memory system, given that we know the form of the memory state. Now, we can also think about H of rho. How uncertain are we about the joint system, given that we know the joint state? Yes?
Question. Is there a difference with, in terms of the units of, I guess, entropy in the bits of information? If we use like UT elementary versus like maybe final log or something, does that mean it's in different units or does that mean equations?
Okay, so if we're talking about an entropic quantity, then we're going to have a log in our measure of entropy. And we get to choose whether we want to make that log base 2, log base e, or log base something else. And the choice of the base dictates which units we're measuring information in. So if we use base 2, we're measuring information in bits. If we're using base e, we're measuring information in natural units or nats. Here, probably we're using, okay, I don't remember, but we can just look up in the paper what base was. We can tell the same story about H of rho. And that'll be illustrated by this blue bubble. Suppose we look at our definition, we say, okay, suppose we take this H of rho, this huge region, and we subtract away this smaller bubble that represents our uncertainty about O. So suppose that we do away with this, we're left with the red shaded region. It has most of all possible uncertainty about S, except this little shared bubble is taken out of our uncertainty because it's information in O and we have access to O. All right, let's see how this formula makes sense in a concrete example. Yeah, probably all of the logs are base E. Suppose that our system and our memory are both qubits that are maximally entangled. In this case, surprisingly, when we erase the system S, we can actually extract net positive work. So our conditional work cost can be greater than 0. This result should be counterintuitive because Landauer told us that erasure should cost work. But we can take advantage of the entanglement, and I'll show how. He says that S and memory will be qubits. And let me pick some arbitrary basis for the single qubit Hilbert space and label it as 0, 1. This will be our computational basis. Suppose that the joint state is maximally entangled. It's one of the 4 Bell states. For example, this one, say 0, 0 plus 1, 1. Since all the correlations that O can have are with S, R is trivial in this situation. Let's calculate the work cost. And see that it is negative. And then we'll see why it should be negative. Oh. Let's see, we have this factor given to us. We need to calculate this. The first term is H of rho. We said that our joint state is pure. The entropy of every pure state is 0. We now need to calculate this term. We said that joint state is maximally mixed. Therefore, the reduced state of the memory is, the joint state is maximally entangled. Therefore, the reduced state of the memory is maximally mixed. And the maximally mixed state has the maximum possible entropy. So H of rho O is 1. We can substitute it into our formula and find first conditional entropy is 0 minus 1, negative 1. So our conditional work cost is negative KT log 2. So indeed, somehow when we erase, the work cost is negative, so we can extract net positive work. And so this result has been called the name of the paper, the thermodynamic meaning of negative entropy. It's entangled systems that can attain negative conditional entropies, because we can know everything about the whole system while being completely ignorant about each subsystem. And I have just a few minutes left, so I won't show the entire protocol explicitly, but I will show you the basic principle of the trick used.
In G, you said that the work is greater than 0, but then the bottom is negative. Is that?
Oh, yeah, sorry, I was thinking about different types of work. So I think we define W of S given O as work cost, right? Thanks. The trick to achieve this result is kind of burn the entanglement. Entanglement is, in a sense, just information. It doesn't intrinsically have energy, but hey, we have a heat source around. So we can put together entanglement with heat, and so extract more work than we spend on the erasure. So here's protocol. First, we extract positive work from the joint state. We can extract 2 units of work. Why should we be able to do that? Well, at an abstract level, we said that the joint state is one of 4 possible Bell states. I would write all this out for you, but again, we're almost out of time. Probably, right? Okay, how many minutes should I finish in?
Okay.
Oh, 10 minutes. Okay, then I will write out Bell states. Okay, first I'll talk about why at an abstract level we should be able to extract this amount of work. So there are 4 Bell states, or maximally entangled states of a pair of qubits. The state that I wrote out to my right, as well as almost the same state with a minus sign, And the same thing except with 0, 1, and 1, 0. We know the form of the joint state. So in principle, we could perform a Bell measurement on this pair of qubits. That Bell measurement would have one of 4 possible outcomes. And we would know the outcome in advance. We would know 1 out of 4 possibilities. So we would have 2 bits of information. We can take each bit of information and feed it into Szilard engine. We can run it Szilard engine twice. And so extract 2 units of work. I can also show you a more explicit protocol for extracting work. Here's the explicit protocol. Let's attribute to each qubit a totally degenerate Hamiltonian, because these qubits have as their resource that we've been talking about only information. They're just information, they don't hold an energy resource according to our setup. So let's call the sole energy eigenvalue E0. Since the total Hamiltonian is totally degenerate, because each single qubit Hamiltonian is, we can unitarily transform our Bell states into the 0, 0 states. Without paying any energy. Because all states have the exact same energies, thanks to the Hamiltonian. Then on each qubit, we do the following. So the energies, again, begin totally degenerate. So here's level E, and let's label this as the 0 state and this as the 1 state. Our qubit is in the 0 state. I'll represent by a dot the probability weight of the state on this level. Now we raise the energy of 1 by a huge amount. So energy level 0 is going to be down here at energy E naught, excuse me, and energy level 1 is going to be way up here. There's some gap delta, which is big. In an idealization, it's infinity. And all probability weight still is on the 0 level. And this looks, on average, costs no energy. It costs no work because the quantum state has no probability weight of being here. So it's like there's no system that's at all really relevant to this. It's like having lifting a weight versus lifting nothing at all. Lifting nothing at all doesn't cost us any work. Next, we thermalize the qubit with our back. The thermalization changes the probability weights into thermal mass. The weight here will come to be what I'll call P0, which is a Gibbs factor. Theta is 1 over Boltzmann's constant times the temperature. We have E0 here and normalizing partition function. There's a tiny, tiny, tiny bit of probability weight up here. P1 is e to the negative beta E0 plus delta. Delta is enormous. This exponential is tiny, so this is hardly any probability weight. Then we take this level and lower it by a tiny amount epsilon. Move this downward just a little bit. And this is like taking a lifted tiny weight and lowering it here. So it's like removing some gravitational potential energy from a high up rock. We'll say that it's the average work performed by the qubit is the probability of the qubits being up here, P1, times the distance over which it was brought down, epsilon. Next, we thermalize the qubit with the bath again. So a little more probability weight will drop, or excuse me, will jump upward. So we have the 0 level here, we have the 1 level here, and now this gap is delta minus epsilon. So now our probability p sub 0, well, the numerator is the same as before, the denominator has changed, and there's a little more probability weight, P1, which is e to the negative beta E naught plus delta minus epsilon over our normalization factor. And this delta is still enormous, and so this E is still really tiny, but not quite as tiny as before. We repeat this process many, many times. This tininess is what makes this process be ultimately quasi-static or approximately quasi-static, so that we're not wasting energy. We're getting out as much work as we can. The result is eventually lower the 1 level all the way down to the 0 level. So again, we have totally degenerate energy levels. But by this point, enough probability weight has jumped upward that the probability weights are distributed equally across the 2 levels. In other words, our qubit has ended up maximally mixed. So its purity, its information content is gone, but we got this work out by lowering the level. How much work do you think we got out from lowering the level?
KT log 2?
KT log 2, yes, our favorite thermodynamic expression. Now am I about out of time?
This is a good place to start.
Okay, so I won't write out the integration for you. You can do it as an exercise. But we do this for each qubit. Each qubit gives us KT log 2 units of work. Total, we get out KT log 2 units of work, and then we pay back KT log 2 in order to erase a qubit. And we have 1 unit of work left over that we get. So that's how we can use entanglement during erasure in order to extract net positive work. Any questions about that? Yes.
So what we erased, so the qubit started in the 0 state, and then it became into this maximally negative state. So the state of qubit is what we erased. Correct?
Are you talking about this process or the overall erasure process?
No.
In the overall erasure process, the qubit started out in a maximally mixed state because it was maximally entangled with the memory. And then in the meantime, we got it into a pure state, and then we got it into maximally mixed state, but then ultimately we reset it to a pure state. So the qubit actually began maximally mixed and ended up in a pure state.
So then what did we erase?
So erasure is resetting an arbitrary state, doesn't matter which state, to simple, clean, agreed upon fiducial states, which we usually call 0. Thanks for listening. Time for lunch, and feel free to ask more questions later.